topic that I've chosen to report is all about mathematics of circular motion. There are three mathematical quantities that will be of primary interest to us as we analyze the motion of objects in circles. These three quantities are speed, acceleration, and force. The speed of an object moving in a circle is given by the following equation. Average speed is equals to distance over time equals 2 times pi times r over t, where r represents the radius, t represents period. So the acceleration of an object moving in a circle can be determined by either two of the following equations. Acceleration equals b squared over r, and acceleration equals 4 times pi squared times r over t2, where b represents speed, r represents radius, t represents period. The equation on the right above is derived from the equation on the left by the substitution of the expression for speed. So the net force F acting upon an object moving in circular motion is directed inwards, while there may be by more than one force acting upon the object. The vector sum of all of them should add up to the net force. In general, the inward force is larger than the outward force, if any, such that the outward force cancels and the unbalanced force is in the direction or the center of the circle. The net force is related to the acceleration of the object, as is always the case, and is thus given by the following three equations. F net equals m times a, and F net equals m times b squared over r, and F net equals m times 4 times pi squared times r over t squared, where m represents mass, b represents speed, r represents radius, t represents period. So, equations as a guide to thinking. An equation expresses a mathematical relationship between the quantities present in that equation. For instance, the equation for Newton's second law identifies how acceleration is related to the net force and the mass of an object. A equals F net over m, or acceleration equals net force over mass. The relationship expressed by the equation is that the acceleration of an object is directly proportional to the net force acting upon it. In other words, the bigger the net force value is, the bigger that the acceleration value will be. As net force increases, the acceleration increases. In fact, if the net force were increased by a factor of 2, the equation would predict that the acceleration would increase by a factor of 2. Similarly, if the net force were decreased by a factor of 2, the equation would predict that the acceleration would decrease by a factor of 2. Newton's second law equation also reveals the relationship between acceleration and mass. According to the equation, the acceleration of an object is inversely proportional to the mass of the object. In other words, the bigger the mass value is, the smaller that the acceleration value will be. As mass increases, the acceleration decreases. In fact, if the mass were increased by a factor of 2, the equation would predict that the acceleration would decrease by a factor of 2. Similarly, if the mass were decreased by a factor of 2, the equation would predict that the acceleration would increase by a factor of 2. As mentioned previously, equations allow for predictions to be made about the effect of an alteration of one quantity on a second quantity. Since the Newton's second law equation shows three quantities each raised to the first power, the predictive ability of the equation is rather straightforward. So the predictive ability of an equation becomes more complicated when one of the quantities included in the equation is raised to a power. For instance, consider the following equation relating the net force to the speed of an object moving in uniform circular motions. F net is equals to m times b squared over r. This equation shows that the net force required for an object to move in a circle is directly proportional to the square of the speed of the object. For a constant mass and radius, the F net is proportional to the speed. So, one is F net is equals to m times b squared over r into F net equals to b squared for constant mass and constant radius. The factor by which the net force is altered is the square of the factor by which the speed is altered. Subsequently, if the speed of the object is doubled, the net force required for that object's circular motion is quadrupled, and if the speed of the object is halved, decreased by a factor of 2, the net force required is decreased by a factor of 4. Equation as a recipe for problem solving. So, the mathematical equations presented above for the motion of objects in circle can be used to solve circular motion problems in which a known quantity must be determined. The process of solving a circular motion problem is much like any other problem in physics class. The process involves a careful reading of the problem, the identification of the known and required information in variable form, the selection of the relevant equations, substitution of known values into the equation, and finally algebraic manipulation of the equation to determine the answer. And consider the application of this process to the following two circular motion problems.